Good morning. Can you all hear me? Okay, so my name is Garrett Slater, and I'm a postdoc at the USDA in Baton Rouge. And about 3 to 4 months ago, I recently finished my PhD at Purdue University, where I was focused on the topic of drones. And drones are sort of this forgotten cast. I mean, when I ask people, when you think about colony health, do you think about drones? And nobody ever raises their hand. And so I'm hoping by the end of this talk, I can really convince you that drones are really important for not only queen quality, but also colony health. Okay, so I've been interested in queen failure for a really long time. So first as a commercial beekeeper in North Dakota, then with the Bee Informed Partnership, and now as a researcher. And one thing I always heard from beekeepers was probably the second most common issue was queen failure. And this is seen in a lot of different surveys or just talking to beekeepers one-on-one. They report that when they buy these queens that they're failing within 6 months when, historically they should be reproducing and thriving for 2 to 4 to 5 years. And so a recent report, I think 3 to 4 years ago, found that 60% of queens are failing within 6 months. Now, a lot of research has really been focused on the queen aspects of failing, right? If the queens are failing, it must be a queen issue, right? But we're starting to realize that it actually may be a male issue, right? The males are always the problem here. We're finding that these poor queens are having poor sperm viability, poor sperm quality overall, and might be related to poor drones overall. And so when I started my PhD, I was really focused on the male aspect of queen failure, and my question is, what's causing poor drones? And if we can identify what's causing poor drones, maybe we can find some kind of applied solution that beekeepers can use in their management practices. Okay, so first we have to define what actually makes a successful drone. And I can really sparse it down to these 3 major points. We have point number 1 is sperm production. This is where sperm is produced for drones. 2, sexual maturity. And then point number 3 is mating behavior. And this whole reproductive lifespan happens during sort of a 54-day period. Now for the first 24 days of development, this includes the egg stages, the larva stages, and the pupa stage. And this is the only point of a drone lifespan where they actually produce sperm. And so there's only a 2 to 3 day window during development when drones actually produce sperm. And so if there's anything that causes damage during this stage, it can actually cause irreparable damage to drone fertility overall. Now once drones emerge as adults, they enter kind of this mooching stage where they have to reach sexual maturity. They just stay in the middle of the colony and they're just tended by the workers. They get fed, they get cared for, they get groomed, and really the drones don't do anything for themselves. But this stage is really important because this is when drones actually reach sexual maturity, and this occurs during the first 10 to 14 days of development. And then after that stage, the drones are sort of kicked off. They're kind of forced to the edge of the colony and forced to fend on themselves. But they do that because that's where the honey is typically stored. And so they can get this high sugary diet so they can actually initiate their mating flights. And so after they reach sexual maturity, they go on these multiple mating flights, and they do this until they either mate or they just die trying. And so when we think about what makes a successful drone, we have these 3 major points. And just remember this throughout my talk is sperm production, sexual maturity, and then mating behavior. And this all occurs during sort of a short 54-day time span. Okay, so first, point number 1, sperm is only produced during development. And so the testes, which is where the sperm is produced, is actually developed during the egg stages. And then once drones reach this larva stage, the testes go bigger and bigger and bigger as the larvae get bigger and bigger and bigger. And the testes development is actually maximized around this 5th instar larva. And so if you ever look at sort of a drone comb, this is when the drones are really large and they're really, it doesn't seem like they actually can fit inside the cell anymore. This is sort of the 5th instar larva. And this is important because this is actually the initiation of sperm production, known as spermatogenesis number 1. And so this is the first stage of sperm development. And then when they enter this cocoon spinning stage, when the drones are kind of upright and their cells are actually capped, this is spermatogenesis number 2. And so these are the only 2 stages when sperm is actually produced for drones. And so it's only occurring through a 2 to 3 day window. And so unlike a lot of closely related taxa or even closely related insects, drones can only produce sperm during this 2 to 3 day window, and they can never produce sperm ever again. And so if you think about from a perspective where they can only produce sperm once, if anything happens during this stage, it can really cause any irreparable damage to drone fertility overall. Now, once drones kind of go through this cocoon spinning stage and go through development, they enter this kind of pink-eyed, purple-eyed stage. And this is, you can see from the graphic, the whole reproductive tract is fully formed. You can see the eyes, you can see the thorax and the wings. And this is when the sperm cells actually develop the tails. And these tail development is really important for not only sperm movement, it's also important for long-term sperm storage and then also successful fertilization. And so really the major takeaway from this first point is that sperm is only developed during this first stage. Okay, so once drones emerge as adults, they stay in the middle of the colony and they receive constant care by the workers. Like they get food, they get temperature control, they get groomed and everything. And this stage is really important because this is when drones are going to reach sexual maturity. Now, unlike a lot of closely related taxa or even like closely related bees, sexual maturity is tied directly to not the initiation of sperm production, it's actually tied to the sperm migration from the testes to the seminal vesicles. And so once drones emerge as adults, they have all the sperm within their testes, but the sperm must actually migrate to the seminal vesicles in order to be used during development. And then once that sperm fully migrates, the drones are really able to initiate mating flights and beginning looking for a queen. Now, these are the pictures at the bottom, the immature versus mature drone. If you ever went to your colonies and popped a drone, or if you haven't before, just squeeze the thorax of the drone and pop out the endophallus, which is that clear structure. If it's clear and there's no kind of brown spot at the tip of the endophallus, that suggests that these drones are immature. But if you squeeze them in and there's sort of white mucus and then the brown spot at the tip of the endophallus, this suggests that a drone is mature. Now, an important point here is if anything happens during the sexual maturity stage, and let's say the sperm is unable to migrate, or something happens where, even though they may produce 8 million sperm cells, but only 1 million sperm cells actually migrate, that's really the sperm that they can use during mating. And so this stage is also extremely important for just overall fertility overall. Okay, then we get to point number 3. So once drones reach sexual maturity, they have their sperm ready, it's high quality, then they actually begin their mating flights. And they go to these areas called drone congregation areas. And these areas are populated by hundreds to thousands of drones. I think there's been some reports of 25,000 drones. And these DCAs are the same DCAs year in, year out. So I know there's been researchers going back to the same DCAs 40 years, and they're using the same locations. And what drones typically do is when they initiate flights, they go on sort of these orientation flights. They go to multiple of these mating licks, and then once they get older, they kind of target one because they're like, well, I better mate before I die because I'm getting older and my sperm's not very high quality. And so they basically choose these based on pheromone cues and visual cues. So what causes poor drones? Just to take a step back, we kind of summarize these 3 major points: sperm quality, sexual maturity, and mating behavior. And they're all really important for sperm quality and eventually try and tie this to queen failure. And so for this talk, I'm really interested in 3 major questions. How much variation is there in these traits in stocks that beekeepers commonly use? 2, are there certain genes that are actually causing this variation? And then 3, is it possible to use these genes to help better screen, to use them for screening for beekeepers to select for these traits, but also use them to improve management practices, such as feed supplements that could be targeted towards improved drone fertility? And so I'll be kind of trying to address those 3 major questions. But your question may be asked, why should I focus on genetics? Well, first, we know a lot about the environmental factors that cause poor drones. We know about acaricides, pesticides, poor nutrition. But I'm really interested in genetics because there's some really robust practical applications for understanding the genes of these traits. And just to take a step back to kind of the broader experimental design, if you go back to your middle school or your high school statistics class, you probably remember this bell curve. I'm sure it's a rough time for everybody. But let's say we sample 100 colonies, and we looked at drone fertility traits from these 100 colonies. We'll typically have this kind of normal distribution where there'll be some colonies produce high quality drones and some colonies will produce low quality drones. And there are likely certain genes that cause these drones to produce high quality sperm. And by identifying these genes, we can have some really practical applications for this. Okay, so first I'm going to focus on point number 1 is sperm quality. And so like I mentioned before, sperm quality is determined not only by the sperm produced during development, but also the amount of sperm that's actually migrating that can be used during mating. So for example, drones may produce 8 million sperm cells during development, but if only 4 million actually migrate to the seminal vesicles, that's all they actually have during mating. So to test this, we use what is known as a common garden experiment. And so as a geneticist, I hate the environment. It makes everything messy, and it's hard to find genes. And so we use what is known as a common garden experiment because we can control the environment to the best of our ability. And so we identified 4 commonly used breeding lines from across the United States, and these were chosen based on genetic ancestry. So for example, how much Africanized genes they had. These are chosen based on stocks that beekeepers commonly use. And they're also chosen based on breeding and selection practices and what type of traits they were selecting for. And we did an early screen. I think we started with 10. We kind of dwindled down to 4 with the biggest differences. And so we brought these queens from across the United States and brought them to a central location in Indiana. And then we raised drones in these 4 colonies. Now, once the drones emerged as adults, we put them to a similar colony with workers that are unrelated to the four lines, because we didn't want the workers to give preferential treatment to certain drones, and then we controlled for all the different environments. Really, the biggest takeaway is we controlled the environment to the best extent, and all the drones were basically treated exactly the same, and so most of the results are probably due to genetic rather than environmental noise. And then we collected drones at ages 10, 14, and 20, and we looked at a variety of sperm quality traits, and we looked at 10, 14, and 20 because drones typically go through this reproductive senescence where sperm quality is really low in the beginning because that sperm is still migrating. It maximizes around this 2-week period and then decreases as drones age just due to natural wear and tear. And we looked at a lot of different traits. We looked at how much sperm these drones are producing, what percentage of the sperm was alive, how fast the sperm was moving. But I'll only be focusing on sperm number because this was highly correlated to a lot of these different traits. And so even though I'm looking at just sperm number, the results can be similar with sperm viability. So here are the results. So here are our 4 different lines, line 1, 2, 3, and 4. The bottom are 3 different ages, 10, 14, and 20, and then we have our sperm number by 1 million. And so 2 million, 4 million, and 6 million sperm cells. And I want you to kind of take a look at line 1 and 4 because these are the ones with the most significant differences. And we see that line 1 and 4 have this senescence where sperm quality and quantity is really low, increases to 14, and then decreases as they age. But what's really interesting is the significant differences, especially at age 14. So line 1 drones at age 14 are producing nearly 6 million sperm cells, which is 2 to 3 more million sperm cells than line 4. Now, once again, these drones are raised in the exact same colony. They're treated exactly the same, yet there's tremendous variation between these 2 different lines. And what does this mean? It means that probably most of this is due to some sort of genetic factor. And so to look at that, we calculated what is known as a heritability score. And so the heritability score ranges from 0 to 1. 1 means that 100% of this trait is determined by genetics. An example of this would be like eye color. We know certain genes cause a person to have green versus brown eyes. Whereas a heritability score of 0 would mean that 0% of this is due to genetics and only environment. We found that 33% of what we're seeing here is due to some sort of genetic factor. Now, while 33% seems really low, it's actually really high for a fertility trait like this. We look at heritability for sperm traits for closely related bees or other taxa, it's usually around 15 to 20%. And so this is actually really, really high. And this means a few different things. This means that the variation that we're seeing, the high quality versus low quality drones for line versus 4, is due to genetics, but it also means that there's a lot of breeding and selection potential for this trait just because the heritability is really high. Okay, we didn't want to stop there. We wanted to look at what specific genes were causing this variation because we wanted to try to use these in sort of a practical application. And so we isolated gonads from about 500 drones and we looked at gene expression patterns. And I'll save you the exact methods, but we found that there was around 1,200 genes in the testes that were regulating sperm production. Now, all genes don't have the same effect. They're usually in what is known as sort of a genetic network. In the outer skirts, these genes have sort of a small effect on fertility, but there's usually some core genes in the middle known as hub genes or master regulator genes that have a huge effect on the trait. And so we pulled out that gene and we looked at what is this gene doing and is it actually influencing sperm production? And we found this gene was called dynein. And the best way to look at this is, imagine you have a boat. The boat is sort of like, we have the rudder and we have the motor. The dynein is the motor for the sperm. So the whole sperm is actually anatomically intact, but the sperm motor just isn't working properly. And if you look at high versus low drones, the drones that are producing low numbers of sperm have lower expression of dynein protein. So it's possible that the motor just isn't working properly, whether there's no gas or spark plug, something's happening with the motor, it's just not working. And so that could be one possible explanation for drones producing low quality sperm. Now keep in mind with dynein, because this will come back in the picture a little bit later, but think of it as sort of the motor for the rudder. Okay, so we first looked at sperm quality, but then we're interested in sexual maturity. So drones must not only produce high quality sperm, but they also must reach sexual maturity so they can begin their mating flights. And so we did the exact same experiment design. It's the exact same, where we had our 4 distinct lines raised in a common garden. The drones are raised in those 4 lines and then transported into one common colony. And then we looked at whether the drones were mature or immature at these 3 different age groups. And so we looked at 10, 14, and 20. And we just measured maturity just by kind of squeezing the drones and seeing whether they had the sperm at the tip of the endophallus or not. And as you can see from a mature versus an immature drone. And so for the graphics after this, I'm only focusing on day 20 because one expectation we have is that all drones should be sexually mature by at least age 14, because that's when their sperm is the highest quality, and that's when they really should be initiating their flight, and just really from previous published research. And so we really focus on age 20 because at this point they should be sexually mature, and if they're not, we could question whether they'd ever reach sexual maturity altogether and just be effective duds. And so we found was our 4 different lines, line 1, 2, 3, and 4, and these are the same ones from our previous graphics. And then we have the percent of drones that were mature versus immature. And so for line 1 at age 20, about 75% of these drones were mature, about 50% for line 2 and 3, and then only about 40% for line 4. Now, this is interesting because, once again, these drones are treated exactly the same in the same colony, the same worker structure, but yet these drones were nearly 40% less mature. Now, there could be some experimental issues with the study. That's why I don't get 100% even for line 1. But even with that, it's still concerning that there's such a high proportion of these drones that were immature. Now, next we were interested, okay, we see that there's, once again, differences between line 1 and 4. Was there genetic differences driving this variation? And then once again, we found that the heritability was extremely high. About 41% of this was due to genetics. Okay, so next we looked at what genes are actually causing this variation. And so what was interesting is we found that most of the genes that were driving sexual maturity were related to the brain expression rather than the gonad expression. And I guess one reason for that is in order for drones to reach sexual maturity, they likely have to go through these physiological changes in the brain. They have to go through these brain maturation in order to reach sexual maturity and then undergo these multiple mating flights. And so most of the clusters that were associated with sexual maturity were found in the brain, and that might be one explanation. And so we found about 825 genes were associated with sexual maturity, and then once again, there's usually genes on the outskirts that have a smaller effect, but then there's usually a few hub genes in the middle that have this huge effect. And so once again, we pulled out that gene and looked at, was this associated with sexual maturity or not? And we found it was known as RAS32. And the best way to think of RAS32, it's sort of the UPS driver that's collecting the gas and the spark plugs and it's driving it all down to the sperm rudder to make it function. And so in order for drones to reach sexual maturity, as you see from this graphic, the drones that are mature are having a higher expression of this. They're producing more, I guess, truck drivers that are transporting this diverse cargo to the sperm to help it swim and function properly. And so it seems to be this really interesting connection between the increased expression of this RAS32, the UPS driver in the brain, to this transportation of dynein in the gonads. Now the question is, if these are happening in different tissues, how are these kind of communicating with each other, right? So if sexual maturity is associated with the brain, sperm production is associated with the testes, how do we get from sort of point A to point B? And so we basically pulled out our 2 networks. So our genes are associated with the sexual maturity, our genes are associated with low sperm production, and then we found genes that were common between them to see if there's some sort of link. And we found that this gene was associated with BCAATL-D, and it's basically the highway that transports this cargo to the dynein protein. And so basically, this RAS32 is being expressed in the brain, it's being transported by BCAATL-D to the dynein protein. Now, just take a step back to kind of earlier findings with the poor quality drones, right? We found line 1 produced a higher number of sperm and had a higher proportion of mature drones. And it could be driven by these 3 genes. Now, what's happening here at these 3 different levels? It's possible somebody's hijacking the UPS drivers or popping their tires, or they're not producing enough UPS drivers, or there's construction or potholes like we see in Indiana with the Baton D, or something happening with the rudder where they're just not getting the nutrients altogether. And so we're trying to make those links, but these 3 genes seem to be extremely important for sperm quality overall. And from a practical application, we could use these to possibly screen beekeepers to help the colonies from not beekeepers, to select for these traits, and then possibly improve management practices to improve the expression of these genes. But that's kind of the practical application of this. Okay, so the first 2 points, we really focus on sperm quality and sexual maturity. But next is flight, right? Mating flights are really important overall. So drones could produce the best sperm, they could be the highest quality, but if they can't find a mate, it doesn't really make sense. And these areas are highly competitive, right? They can have thousands to 25,000 drones in these areas, and they're constantly competing with each other. And so we next looked at, okay, we see this variation in these sperm traits, but is there a tremendous variation in some of these flight characteristics? And so we did our same experiment design, our common garden experiment, but instead of just putting drones into a common colony, we actually put these small RFID takes on the back of the drones. They're very lightweight, they don't affect flight at all, but it allows us to get some really important characteristics about flight behavior. So it doesn't really tell us a lot about mating, but it tells us when the drones are leaving, when they come back, and it gives us a good opportunity to understand what the drones are doing during these mating flights, like how long they're flying, when they first fly, and how many flights per day are they taking. And this, the far right graphic, this is a single drone I tracked, and this is kind of what the RFID Take data looks like. And so this is a drone, for example, with the first 4 days, it didn't really do much, just kind of hung out in the colony, and then after that, it flew for about 20 minutes per day. And you can see on day 15 or 16, it's actually a rainy day, and so the drones were unable to fly. And so it gives us some really cool information about some of this flight data that we can hopefully associate with some of this mating behavior. Okay, so here are our flights. So we first looked at age of first flight. And so this is an important characteristic because we'd expect that when drones actually initiate flight, this should be highly associated with not only sperm quality, but also sexual maturity. And so what we found was at line 1, these drones didn't initiate flight until around age 8, whereas line 2, 3, and 4 was around 6. Now, 2 days in a drone's lifespan is massive. And so for line 1, for these drones to delay flight for an extra 2 days is really interesting. And one reason for this may be if they actually kind of mooch on the workers a little bit longer in the colony, they can improve sperm quality, they can improve a lot of quality measurements. And so that might be one reason that they have higher quality sperm, is just because they're delaying flight an extra 2 days. Now, flights per day, we found that line 1 flew around 10 flights per day, 8 for line 2, and then 6 for line 3 and 4. And so we also saw a lot of variation in how many flights they took per day. And this was just the RFID Take data gives us a lot of different flight characteristics, but these are probably the most interesting. But the overall takeaway here is that we saw a lot of variation in not only these sperm characteristics, but also these flight characteristics. Okay, just to summarize, we found tremendous variation between our 4 breeding lines for these 3 major traits: sperm quality, sexual maturity, and mating behavior. We also found that they were highly heritable, and we found certain genes that were likely driving this variation. Now, from a practical application, we can likely use this for sort of a screening tool or possibly to improve supplements. Now, there's some important considerations to take from this study. The first is, we didn't really make the connection between poor drones and queen quality, and I think that'd be a really important next step, right? But that's really the big issue: what's causing poor queens? And so, trying to make that link between poor drone quality and queen failure, I think, would be kind of an important next step. And I think the next thing to think about is that performance may differ based on location. And so even though some of the results may just seem very alarming, I just want to take a step back and just take it with a grain of salt, because this was only done in one common environment in Indiana. And so even though line 1 performed really well in Indiana, if we repeat the study in, let's say, Nebraska, Idaho, Florida, California, line 4 might actually outperform this other line. And so it's important to really take into account that we can't always reduce everything down to just a genetic level, that there's a lot of environmental things that are driving this, especially with some of these drone traits. And so this study has to be repeated in multiple environments to see if this is still true. And the last thing is, just to kind of consider, is breeding for production or even viral defense behavior may have a negative impact on fertility. And we see this with a lot of other livestock. When you breed for milk production or other production traits, we always see a negative impact on male fertility specifically. And so it's possible that beekeepers are breeding for some of these production or viral traits, that this may have a negative effect on male fertility. Now, from an industry perspective, I'm assuming probably production and viral defense would probably take higher priority than male fertility, and so that may just be a trade-off you're willing to deal with. For me, I'm really interested in trying to kind of tease apart those mechanisms so we can try to select for both concurrently. But that's just something to consider with some of these results. And with that, I want to thank my PhD advisor, Brock, Crispin, and Austin for the bee work, and then my funding partners, especially the North Dakota Beekeepers Association and Department of Ag, the Foundation for the Preservation of Honeybees, Project APSM, and then Purdue Egg Seed. And with that, I'll take any questions.
So I've got a question for you. How do you tell the difference between a 10-day-old drone, a 14, and a 20, so we can test the viability of the 20-day-old drones?
Yeah, for me, I actually paint marked them, and then I put the RFID tags on them, so I was able to know how old they were. But I mean, for a beekeeper, that might be a little bit more infeasible, right? So,
so how do we do it?
Yeah, that's a really good question. I think one way to start is starting maybe at a university USDA level where we're actually selecting for that stock, and then we could actually transport that out to the beekeeper. If a common beekeeper was interested in that, maybe like a service such as the Bee Info Partnership or some other outside service, because this is a really hard thing to measure. You need special equipment to actually measure it. And so I know the cattle industry, they actually have people that do go out and measure fertility with like an iPad. You just collect the sperm and put it into like a machine. But I don't think the bee industry is quite there yet, but maybe eventually. Yeah. But still, the age problem is always going to be the issue.
So we just have to keep popping them and see.
Keep popping them, yep. I guess you just measure maturity rates. You just keep popping them and see how many mature versus not mature. That would be an easy way.
Yeah. All right, thank you.
Hey, Sam.
Hey, Garrett, thank you. That was awesome. In your opinion, do you think the practice of collecting drones for instrumental insemination rather than the competition of natural mating flights could decrease their fitness over generations?
That's a really good question. I would guess it might. It might actually. I can't say for certain, but I guess there are some trade-offs. So if you're selecting for certain traits, such as production and things like that, you're going to have to do some sort of closed mating population. And that may have a negative effect on male fertility. And so that's could be one possible driver.
So I'm kind of just wondering about when you said that lower quality drones get more care from the hive, why is that? I would think that they would want to boost the ones that are already strong and have good genes.
Yeah, that's something, so Zachary Huang out of Michigan State did some really cool studies where they found that if the drones were, they raised drones in worker cells versus queen cells, so the ones in the worker cells are supposed to be lower quality, and they actually stay in the colony longer, they receive more vibrational signals and more of this other care. And so it's possible that the drones are kind of selectively choosing the ones that are lower quality just to get them up, because they've already produced this certain number of drones, so they want to maximize reproduction for all of them. But it would make sense for them to kind of target the high reproducing ones, but I guess they already produced them, so they're trying to get them up to that point, I'm assuming. But
okay. Thank you.
Thank you.
Hi, I've lost my voice, I'm sorry. But in your experiment, did you always do drones in the spring, or do you notice throughout the summer the drones sperm quality changes based off food supplies? How did you set that up, I guess?
That's a good question, yeah. So I did it twice. So I did it in Indiana, and I did it in early June and then kind of mid-July. And so I only did during those two kind of seasonal differences, but I didn't do year in, year out. So, in Indiana, our nutritional sources are different from the spring to the fall, and so I would expect that there might be some differences with that, and there might be some differences between the lines too.
How you doing, Garrett?
Good.
Mark here. Just to comment on the gentleman asked about finding mature drones. I don't do instrumental insemination, but a lot of people I know do, and what they're doing is to increase your chances of getting a mature drone, they're waiting till 11 or noon. When it's good for mating, the drones are flying out and they're putting a type of, either an excluder on front of their entry, and then come 2 in the afternoon, 3 when it's starting to cool, those drones that are coming back in, those are more likely to be your mature drones. And so they're trying to select from those. I'm sorry, I cut line. I didn't see you there. So that's where they're really selecting most of the drones from. They have a much higher chance of getting mature drones if they've just come in from their hopeful to pull off a mating flight. So if anyone's doing that, good luck.
My question would be to ask you if you took nutrition into account, and what type of nutrition did you provide for these drones during the experiment, and did you consider that portion of it? Because I would believe that would have a lot to do with it as well.
No, that's a good question. And so in the beginning of the spring, I think we got everything in I guess, April and May in Indiana, and then we just kind of equalized all the colonies. And I think we gave them like one protein supplement in that early stage. But then after that, I think we did like one kind of oxalic acid mite treatment because we want to try to eliminate all these different environmental factors. And then after that was this kind of natural forage. And so kind of getting back to the previous person's question, if we're only measuring this during certain times of the year, it's possible these nutritional sources could affect drones differently, right? And so if we do it in May versus June, like the floral sources are different, and that could drive differences in the drones.
So very little or no additional supplemental feed?
No, not during the experiment. Yep, no treatments, no nutritional supplements during the experiment. Yep.
So drone infertility has been positively linked to neonicotinoid exposure, which are neurotoxins, which sounds like it would mess up the UPS driver. In your example, did you consider that research and look at that or do any testing? I know by your sponsors, maybe you didn't.
Yeah, so I was really focused on the genetic part of it, and I think I need like another PhD to do some research on that. I know there's probably some other universities kind of focus on the environmental factors. I think Juliana Rangel has done some studies with amitraz, and I'm not sure about neonicotinoids. I think maybe Jennifer Berry has, but we do know that they do have a huge effect on drones, especially since drones are really sensitive during these two stages. So I'd like to kind of focus more on amitraz, because if sperm is only produced during those 2 to 3 days of development, and there's a lot of amitraz usage or some kind of exposure, drones can never repair from that damage. And so it'd be kind of interesting to look at that developmental part and see what type of exposure they're receiving and how does that impact drones really long term.
You're in Indiana.
Yeah, in Indiana, yeah.
Two questions. How many drones we need for each queen for mating? The second question, the effect of virus on the drone on mating.
The violence on the drones? Was they checking? Okay.
The virus.
Oh, the virus on the drones, okay. Yeah, so for the first question, we had 3 colonies per line, and so I guess we had our 4 lines, and then we had 12 total colonies because we had 3 per line. And then from each of the individual colonies, we had 150 drones per colony. And so I think it's like 450 to 500 drones per line total. And then as for the viruses, we didn't check any viruses at this point. We made sure when the drones were emerging that they had no viral mites and no overt signs of some of these viruses, but we never specifically tested the viruses. Thank you.